Hello, everyone. So, today we are here to talk about how we are providing AI compute environments for different, like multiple diverse units across the organization, Nokia, um, and with how we do it on Kubernetes environment specifically. So, yeah, my name is Gautam Moktan. I work as a system architect in NESC. I'm looking over the AI/ML platform services, making sure our private cloud environment and infrastructure is ready for AI/ML workloads for our users. And
Yeah, I'm Zhang and work as a system architect at NESC, mainly focusing on Nokia Kubernetes service.
okay, so maybe a little bit about what is NESC. It's Nokia Enterprise and Services Cloud. We basically have infrastructure as a service. We have a lot of our own hardware distributed across the globe, over 6 data centers, 4 edge locations, and on that hardware, a lot of servers and switches and racks. We have OpenStack deployed. We have storage provided through Ceph. We have Kubernetes clusters, like 320,000 cores dedicated to Kubernetes clusters that runs on Talos-based OS. And we also have a netbox for all of our inventory management and source of truth. And so as you can imagine, lately we have been gathering up a lot of GPUs as well. Though it's very tight to find from the market. Also, there's a lot of demand, but still, and we have been growing almost double every year on our GPU capacity. Currently, we have a bit more than 600 GPUs, but yeah, that's what we're increasing, and it's very expensive investment. CapEx is there, so we want to make the utilization quite heavy because it's CapEx investment. We buy it, so if we are not using it, it's a waste. So these are the challenges. How this talk is about how to improve the utilization and make people share the unused capacities on it as well. So basically, what we do is we bring in the GPUs, just like it's built in the servers. Basically, when we buy servers, it's in the GPUs are there in the servers, and we install them on the racks in our data centers, connected through our own network, and then on that the deployment happens for whether it's Kubernetes, different kinds of platforms that we provide to the end users, and then that's where our in-house automation kind of takes care of provisioning them for the end users. The account management, monitoring, and all of those stacks take care of the whole infrastructure as a service. And then we onboard users on top of that, which are basically different R&D units, different business units, different product development units, and whatnot. So as I showed earlier, we have like more than 6,000 different projects running on in that infrastructure. So these are only the the part of what we maintain. There's also a lot of consumption of the compute on different other public clouds and whatnot as well, and labs. So on this side, so much of our work revolves around making sure the infrastructure. We work on the infrastructure setup side, the cabling of the hardware, the validation of the hardware, drivers, plugins, and whatnot to make it fit into the automation stack. And after that, also there's in this new the AI specific work, there's a lot of work also we get involved in to work with our end users, the projects, for making sure that they have all the other complementary services also, so that they don't have to rebuild everything for every project. So there's a lot of reuse of the common components as well in that. So we provide a certain common stack if they choose to use. Of course, it doesn't fit all teams, but it helps a lot of the teams. And that also saves a lot of time and resources. But also the central piece, the dynamic capacity provisioning, is where we are working heavily on how do we give different amount of GPUs capacities to different teams. So my colleague Kai will cover the infrastructure setup first, and then I'll go on the Volcano KubeRay bit after that.
Okay, so the infra setup. So the core part of this NESC infra service here is powered by the Nokia Kubernetes service, which is the NESC managed Kubernetes service for the end user, as well for the NESC hosted service like AI platforms. So NESC manages like several layers from infra and the Kubernetes. So from the infrastructure, the computing resources coming from either OpenStack VM-based or baremetal-based resources with Ceph-based cloud storage for the PVCs and the DC networks for the connectivities. So on the Kubernetes layer, NESC will provide the managed clusters with certain plugins for storage and networks with monitoring and logging stack. And for the GPU devices, those will be installed as the GPU workers with needed container runtime and kernel module and drivers with pre-installed GPU operators for GPU use case consumption. So if I go to the next slide. So to facilitate the bare metal Kubernetes cluster, we redesigned the network architecture. It is now runs with layer 3 only. So it's a BGP everywhere, including the host. So host is participating in the BGP routing, which means we break the rack boundary. So all the servers in the same data center fabric is like modeled into one server pool. So we can allocate servers from any racks to form a cluster. That brings the great flexibility for the cluster creation and also for the cluster scaling. We use the open source Netbox tool for DC data center inventory as a source of truth. The screenshot here shows an example of how we model the GPU card in Netbox. All the data center configuration, including the servers, the server cabling, IP address, and the cluster ownerships are all modeled in the Netbox. All the automation we build is on top of this. NESC also runs we call it GPU supercluster. It's a liquid cooled in the data center with a high performing GPU backend fabric. So, and every server here in the cluster has 8 NVIDIA B200 GPUs, and every GPU is paired with one dedicated 400 gig NIC for backend communication. And they are all cross-connected through 8 backend GPU switches to provide fast inter-GPU traffic across the node through the ROC v2, the RDMA over converged Ethernet via the routed network. So, of course, they have the front-end NICs for the normal traffic and storage access. And at the moment, the cluster has 64 GPUs, but with this one strip, it can scale up to more than 1,000 GPUs in the cluster. So in NESC, how we provide GPU as a service, how GPU are exposed to the users. So the majority use case coming from the encased metal, it's the bare metal Kubernetes cluster. Those GPU worker nodes with Talos Linux installed, with GPU kernel module driver built-in. On top of that, there's a GPU operator installed to expose GPU either as a whole or as a slice. Then the pod can consume them. Also, we provide like bare metal as a service to install the Linux as choice of user on those bare metal servers. Then user get access to them through the SSH keys. Then they can do whatever they want. That is a small part of the use case. Also in the working in progress, we provide GPU also for the OpenStack VM users as a whole or as a slice. Maybe it's worth to mention the latest NESC OpenStack is also running on top of bare metal Kubernetes clusters. So we talk about we have a single server pool in one data center to model all the devices, all the hardwares. Like here are two examples. So every hardware configuration is modeled as we call it node flavor. So we can see like one flavor has 8 NVIDIA GPU, another flavor has 8 AMD GPUs. So when we create a cluster, we can define amount of nodes from each flavor. Then those selected nodes will be like created as a Kubernetes cluster out of those. So GPU could also be like in every node we can expose the GPU as a whole or as multiple instances from the NVIDIA technology, like multi-instance GPU, MIG instances. So after configuration through the GPU operator, they are exposed as Kubernetes node capacity. Then the pod manifest can create the request. Then the scheduling will choose the matching capacity, matching node with the capacity for those workloads. I think that's the infra part. Let's switch.
Thank you. So with this, we bring the hardware to ready for serving to the end users, and then now the challenge is about like, okay, which team gets how much capacity and such. The stark difference between the public clouds is that in the public cloud you have a credit card associated with an account, and then it starts consuming from there depending on your consumption. So credit cards is charged. In an organization, it doesn't work that way. At least not in the way that we're working. It's basically approval. This team gets approved for this much, and this team gets approved for this much for this duration, or this project gets approved for this much till the lifetime of the project. And prioritization happens, left and right also, right? Escalations and such. But in general, the usage landscapes, then those teams come in, and then they have some particular use case in mind, some AI use cases, and then that can be agentic or use case, or they are training, pre-training a model, fine-tuning, or just LLM serving. But also that comes along with it, a lot of data services requirement, because the source of data can be different for each of them. Then there's a lot of governance around the data, enterprise data especially, and also geographic limitations around that. So based on that, the requirements for compute capacity, let's not talk about the storage capacity, but also that is something to keep in mind. But in this scope, the compute capacity is vastly diverse, and different teams will use differently. So we generally try not to bother with what is the use case, right? Because we are the infrastructure provider or the compute capacity provider. So our customers are pretty much we interface with the teams that consume our capacity, or the teams that say come with like, hey, I have been approved this much capacity, so give me that. So how do we do that? And this is where it starts, the challenge starts forming here. It's like, okay, so this is one site, one of our site, right? We have multiple geolocations at different sites. So in one of the site, let's say this has 58 servers. I just visualize this. Some servers have 8 GPUs, some servers has 2 GPUs. These are our typical configurations. The 2 GPU ones are PCIe connected. The 8 GPU ones are the HGX, or in AMD speak, OAM modules. So these are the configurations of the server. So you scale, you either give the whole server, so you either get 2 GPUs at a time or increment with 8 or 2, depending on the availability. And that's what the automation is working on at the infra layer. And then when you are creating Kubernetes cluster, you still need the control nodes, which you don't want to use the GPU nodes, expensive GPU nodes as control nodes. So there's a separate, we use 3 CPU-only nodes for each of the Kubernetes cluster. So then we start breaking it into different Kubernetes clusters, and each of them will have their 3 control nodes. Yeah, there's already optimization opportunity there if they could use the same control nodes. But then the main thing is about the GPU. Again, the most expensive resource, the finite resource. Especially when the demand is so much, we can't even go to the market and say that, hey, I want a GPU server today, and then ask a vendor. Vendor one says 6 months, another one says 8 months, another one says, we're not sure today. So in that scenario, we really want to improve the utilization. And as I said, because we don't work on the credit card against consumption build against credit card approach, it's really tricky how we control utilization, how the usage. There might be some tenants, we call now the customers, end users as tenants. Some tenants who are overshooting are like really pushing the compute GPUs and utilizing all, and they are asking for more. But at the same time, another tenant is not using as much, but they have been approved and they are like, this is ours and we might need it tomorrow, next week. Our project hasn't started today, so that's why, but I'm not giving my GPU to the other team. So various reasons, right? Enterprise, large organizations, that kind of problem exists. And then one way to solve it could be that, okay, so how to make this happen would be if we had autoscaler, cluster autoscaling, then that would autoscale on demand, so that unused capacity would be released into the pool. But again, as I said, the approval way of handling capacity kind of doesn't work in that scenario. And then what happens is that people think that it's risky for their project if they scale it down, and because it's a limited finite pool, when they actually want it, what if the whole cluster is saturated and they can't actually get the capacity and their project is at risk? So another issue is that they either have to scale the whole node. They can't say like, I just want one more GPU. So at least 2 GPUs there. So because of that reason, so then we thought like, okay, let's make the whole cluster bigger. First of all, we save on the control nodes, less control nodes needed. When you take the whole and then just assign the same control node for the whole set of worker nodes. And that means, and the people are using, tenants are using namespaces, then in this example, the tenant E actually could be, the workloads could be using the, be hosted on the, be scheduled on the other unused nodes. Okay, so then the whole, let's do, leave those 2 as special cases. They don't want to be part of that one. They have a special privilege. But then the rest, if you make it into a common pool, and these people use their namespaces in that way. But the problem with namespace only is that it only has an upper limit. You have a resource quota or upper limit. There's still like first come, first served. There's no preemption. So again, when the cluster is saturated, there is no guarantee that you will actually get a resource when you actually need it. So the teams are again incentivized to let the deployments run idle than risk coming back in a saturated cluster, and that's what I'm calling this, the economic principle, or the term tragedy of the commons, that people are trying, actually they are independently and rationally acting, but overall the whole organization suffers because of unused capacity, and that's this resentment towards us. How do we make that problem go away? And that's where we were thinking. So let's see, if we make people use Ray clusters specifically, most of these people are using Python anyways, and Ray is a very good framework for processing AI workloads, especially Python. It covers all. And if we onboard them to Ray, Ray does the work of auto scaling down when the workloads are sitting idle. The pods are scaled down, called down, so that the resources are released, so the deployments can't sit idle for a long time. So that is released, and then the risk of saturation still remains. So because people are still like, if it scales down, then how do I guarantee that my project, I can say that I will give it today, but then next week my project has a deadline, and then I plan to do it on the weekend. There's no guarantee that when I go there, the cluster will allow my pods workloads to be scheduled. And that's where we found the Volcano to help us with its hierarchical queue management. Of course, Volcano is this batch job scheduling system. It's like an alternative to the Kubernetes scheduler. It has some other additional features to the Kubernetes scheduler, like gang scheduling, which is also already adding us a benefit, because without the gang scheduling, what we would have is that if we have a cluster that has 2 GPUs available, but then a person sends 10 GPU requests, the first 2 GPUs would be assigned, and then it will be stuck in the pending state. And then any other person who comes later and asks for 1 or 2 GPU would still be blocked because the first one is there. But with gang scheduling, it will just evaluate, like you wanted 10, there's only 2 available, you stay in the queue. So it's either the whole set resource fulfilled and scheduled or not. So those kind of features are also there. That's also, again, geared towards the utilization improvement. But the main focus here is the hierarchical queue management, because we are still trying to solve the problem with the approval-based thing, people wanting to avoid the risk and having some sort of guarantee. So what we did here, so Volcano provides, when you define a queue, you can specify the capability, deserved, and guarantee values for the particular queue. So you can set up, there's a queue in the Kubernetes cluster, the 58 node cluster that we saw earlier. That has, you can put multiple queues, and different queues have different kinds of capacity. One might have 10 GPUs, nvidia.com/GPU defined as 10. The other might have 5, and then so on. So in that way, if you divide it like that, you can also define, so you can define the deserved values like that. That would be the assigned, the approved capacity that the team gets. But also on that one, if they really want to guarantee that when they come back, even when they're idle, they can also be specified guaranteed values, so that when they come back, even if the whole cluster is saturated, but they did have a guarantee value in their queues, some other guy will be evicted out and their pod will be scheduled. So that suddenly makes the whoever is the capacity owner of that team, the manager, is like suddenly willing to, okay, this now means I don't have to risk my projects. So that's was the thing that we wanted to leverage. So what we manage from the infrastructure side is we give out the top level queues from the root or parent queue in Volcano, define those. We try to set, so actually I probably should have explained the guarantee here. So we try to set the top level queues, and that means when the additional benefit is that even if you have been given 10 GPUs out of 58, or like, out of 100, for example, if the 10 is your deserved value, you can overshoot that as long as the rest of the cluster is still idle. So you can still overshoot that all the way up to the capability value. So that means, as you can see in the tenant B, The tenant B, the orange one is, let's say, their deserved one, but their workloads can overshoot their deserved capacity and still consume the GPUs from other worker nodes as long as there is idle capacity. But when the cluster starts to get saturated, all of the tenants start converging towards their deserved values, and which is kind of then people kind of deem that fair, and also it brings the benefit of utilization to the rest of the whole cluster's utilization level goes up. Yeah, so that's the social contract that we kind of found that and then we did also, talk with a lot of teams on what are the other options. There are corner cases where it doesn't fit, and also as Kai mentioned, we do have the baremetal services based GPU. Some teams require that. The OpenStack based GPU access, that's also valid for some of the use cases. But for many of the use cases, AI use cases, and especially Python and Ray working very nicely. So this is working for us to alleviate the pain of this finite and very expensive GPU compute and sharing interdepartmental resource sharing in the organization. So what we implement there, this is basically we do we develop an admission controller that will inject the Volcano scheduler for any jobs or workloads that come into the cluster, and they assign it to the particular queues that they belong to, and these are based on the identity and authorization token that comes along with the jobs. And we also have a namespace-based filtering, so it does that so that it only manages those namespaces. It doesn't try to manage other things, so that the out-of-band resources are set aside. And then users can log in through the same portal. The end users, the platform owners, but then the end users, whoever is the app developer, can also log into the same one and get the service account and the kubeconfig access credentials through the same portal. And what we do is we just okay, you have a deserved quota. You have here's your top level queue. And you can decide, you are the pool admin of this quota. You have 10 GPUs. If you want to divide it to dev and prod teams or any sub queues, you can do that. Then you can define your priority in those ones also. You can set your own deserved for each of those sub queues. You might have sub units that have bundled together towards us. So what we do is basically on the deserved is an approved queue. From us, you can set whatever you want in your sub queues. Capacity is, you get a minimum of, double of your deserved that you can overshoot to. You can overshoot all the way to twice your deserved one. But also, if you have your deserved is more than half of the capacity, then it doesn't make sense. So we cap it to 90% of the cluster, so the cluster has breathing room. And then the guaranteed, we try to make it, to default 0, and then unless there is a super escalated exception, privileged exception. But yeah, so but then they can do guarantees themselves also in the sub queues. And CPU memory, comparatively, because those are low investment resources compared to GPUs, we just make it okay, you get proportional for we calculate the sum of capacities for each resource type in the cluster, and then make the CPU and memory proportional into those queues, because the primary one is the GPU is the primary driver for that. Yeah, so, and then after that, what happens is both the Ray cluster, whether you deploy a Ray cluster or you deploy a namespace, create a namespace, they are tied to the particular Volcano queue. The Volcano will control anything that comes to a namespace. Is, as I said, the admission controller takes in care, and then that admission controller will assign, okay, this is coming for this namespace, it is part of this Volcano queue, and then it injects that, and Volcano takes care of managing the priority, calculating the scheduling breathing room, and then eviction if required, prioritization, calculating the weights and such. So, and similar with the Ray cluster also. With Ray cluster, when we deploy the Ray KubeRay operator, we tell it that, okay, remember there is a Volcano scheduler here, use that one. And then after that, Ray cluster also takes that, so that when the Ray job is sent with number of GPUs 10, then the same gang scheduling is taken care of. So that solves the problem. And after that, it's in the namespace. Then in the namespace, users can deploy any of these things that whatever they want, right? So, but we also are making this available slowly so that users can click something and deploy automatically there from the same portal. So it kind of is like a backstage kind of a platform, but this is more, let's say, tied to the AI ML space and more like a marketplace where people can just get started easily and pre-tested and validated deployments of these AI ML components. So this is what we are trying to build and we are building as we speak and releasing a few of these features one at a time into our releases. This is like 4th release of this tooling, and then this enables our end user driver to kind of view this setup as their AI factory, one-stop AI factory. They log into the AI factory as a new data scientist comes in, logs into the AI factory. They know what is their approved queue. They select, I want this deployed, goes into their approved queue of their corresponding unit, and then they get started. So that's pretty much, but then the details of this, maybe that is a topic for a different session. But yeah, thank you.